Okay, this is just an overview video. It's not meant to be any kind of tutorial. If there is interest in this project, I can do another video with more detail. Basically, a few years ago, CNC converted my Bridgeport mill. Got some ball screws and ball nuts from Taiwan. I found this guy on a forum. I'll have to dig for his contact information. I had to ground mail him a check, and then he sent me these ball screws. Put the ball screws, replaced the Acme screws on all three axes in the Bridgeport. Here you see I got a ruby tipped probing head, and there's a Mach 3 plug-in where you can kind of use your mill as a coordinate measurement machine, sort of. It can also be used for just finding the zero on a part you're about to machine, but I found that it was kind of too big of a pain to switch to that probing head every single time, and I just picked up on the edge in other ways, but could have some uses. Here we are just showing the functionality of the built-in Mach 3 rectangular clearing. The last pass here is kind of like a oval-shaped pocket there. This is just another basic video where we're doing circular interpolation. This is kind of one of our first tries at cutting a large circle on the mill. For anyone that's got a manual mill and a dicey rotary table knows it's kind of a pain, so it's pretty nice to just be able to put a part in and use the circular interpolation to cut a circle. Sometimes when you CNC convert a mill like this and you do a circle, you'll have flat spots at the 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock positions, because usually what that's because of is there's too much backlash in your X and Y ball screws and ball nuts. The ones that we got from Taiwan were a pretty tight fit. Mach 3 does have built-in backlash compensation. I can't remember if we were using it or not, but we only had a couple of tenths of backlash, as I recall. And I think that the backlash compensation was giving us some trouble. So because our ball screws were pretty darn good, we just ended up turning the compensation off. And yeah, if we needed to make a really, really circular hole, we would maybe rough it in with the XY circular interpolation and finish it up with a boring head on the mill or something like that. Here we've attached a DeWalt router to the quill on the mill because the Bridgeport spindle can only go up to, I can't remember how many RPMs it is, but I want to say like 1300 RPM, something like that. The DeWalt router can go up to, I believe, 22,000 RPMs. So this is a kind of a requirement if you want to use a very small end mill like this one here. You can see, I think this is a 1/8 diameter end mill. So if you're going to be cutting anything with a 1/8 diameter end mill, the RPM's got to be pretty darn fast, or else you're going to have problems. Here we are just cutting out like a logo and a piece of aluminum. There's a helical plunge cut. So if you're going to be plunging with the end mill, it's pretty hard on the end mill if you go straight down. So you'll see a lot of routines where it helixes in so that the chip load on the end mill isn't so bad. We were just cutting into Delrin plastic here, so it was more just to try out the feature than anything. We probably could have plunged right into the Delrin. And here we're cutting out an internal sprocket. I guess you'd call it a sprocket. Internal ring gear, internal sprocket. The form is more like a sprocket than a gear. We were going to make a fourth axis rotary table with this and basically a timing belt. I have the CAD designs for it someplace. We never ended up making it, but this, we were just kind of messing around, testing out the functionality. Here's another video showing the adaptive clearing routines. Basically, they can be generated in CAM software to clear out a lot of metal while still not heavily loading the cutter. Here I am making a toy, not really a toy, more like a decoration for my kid's birthday. Don't remember what number birthday this was, but this is one of those things where it's a cube inside a cube inside a cube. You've probably seen them online. And finally, this is just a video showing, it's kind of boring, but it's basically comparing the position that the Mach 3 is telling the mill to move to with what the glass scales on the digital readout are actually hitting. So these two systems, the digital readout and the Mach 3 servo control system, are completely isolated from each other, but you can see that they're repeating very well. I think that digital readout is the accuracy is 0.2 or 5 microns. So I'm sure I picked probably a best case scenario. I don't think it would repeat quite this well every single place, but there it is. Thanks for watching.